Welcome to the first video of our second class set of video recordings. We ended last time with a discussion of how we classify covalent types of bonds versus ionic. If you remember, covalent bonds can have differences in electronegativities between the two atoms of anywhere between 0.1 to a full 2.0 in terms of a difference. And it's useful to have an understanding of the electronegativities of atoms that you frequently might find in organic molecules, just so you understand if there is a type of dipole that is present, and for you to be able to assign it, because many times dipoles factor greatly into how molecules react. A lot of attraction is electrostatic attraction in organic chemistry. So to test, we've got this molecule of hydrofluoric acid, HF. We can see that fluorine's much more electronegative than hydrogen, so we draw a dipole arrow indicating that the hydrogen's electropositive. So the cross of our dipole arrow starts around the hydrogen. The difference in electronegativity is 4.0 minus 2.2. So we've got a difference of 1.8, and that indicates we've got a polar covalent bond. Of course, HF will ionize in a polar protic solvent, such as water. Here we have drawn one of the lone pairs of electrons on our water's oxygen atom going to form a bond with the hydrogen. So we're using a double-headed arrow drawn towards the hydrogen atom, and if we form a bond to the hydrogen with that pair of electrons, we have to destroy this bond between the hydrogen and fluorine, so we put those electrons onto fluorine, and in the process we generate H3O plus and the fluoride anion. And what's interesting is we all know, molecules, atoms react to form a stable octet of electrons. We can see, or a closed shell. We can see in the case of fluorine, we've got 3 electron pairs and 2 electrons in this bond for a total of 8 electrons. Hydrogen has its 2 electrons filling the N equals 1 energy level. In water, we have a full octet, 2 lone pairs of electrons and 2 bonds, so a total of 8 electrons. Now, it's kind of interesting to go from, calculating our full octets to being able to assign formal charges. So you can see this oxygen in our H3O plus, it has, by virtue of sharing, a total of 8 electrons. So 3 2-electron bonds is 6 electrons plus 2 electrons as that lone pair. And so even though it has a full octet, it still gets a formal positive. How do we figure that out? How do we assign these formal charges? Well, a trick is oxygen has, in its neutral state, a valence of 6 electrons. And so we count up the total number of things oxygen has when it's found in a molecule, and we count electrons as a thing, and then we count each bond as one thing instead of 2, even though each bond contains 2 electrons. So in this H2O, our oxygen has a total of 6 things. So 4 electrons and 2 bonds for a total of 6 things, and that's the exact number of electrons that oxygen would need in its neutral valence. If we do the same, perform the same function for the oxygen in H3O plus, we count a total of 5 things. That's 1 fewer than the 6 valence electrons, or 6 things that oxygen would need to be neutral. So because we're 1 fewer, we have to add a formal positive. Similarly for fluorine, fluorine has a valence of 7 electrons in its neutral state. We've got 6 electrons, 1 bond for 7 things. That means this fluorine is neutral. But over here we have 8 electrons, so 8 total things. That means that fluorine has a negative formal charge. So if you didn't get that, we'll go over it one more time shortly in the future. For a Lewis dot structure, it's important to show all the valence electrons to help keep track of them. So let's take ammonia, NH3 as an example. Nitrogen has 5 valence electrons. Each hydrogen brings 1 valence electron to the table. We've kind of aligned them nicely such that we can combine 2 electrons into bonds between the hydrogen and the nitrogen. So here we go. We've got 3 nitrogen-hydrogen bonds and 1 lone pair of electrons on nitrogen. And of course, ammonia is a Lewis base. That's an electron pair donor. How about methane, CH4? Well, carbon has 4 valence electrons. Each hydrogen brings 1 valence electron. We kind of align them well to form 2 electron bonds. We can see, oh, carbon's got 4 bonds to hydrogen. That's 4 things. It's neutral as CH4, and it's got its 8 electrons. Just like nitrogen has its 8 electrons and a total of 5 things in this ammonia Lewis structure. How about BH3? Boron's kind of an interesting actor. It has 3 valence electrons. We pair each of those with 1 valence electron that hydrogen brings to the table, and we get our BH3. It's a Lewis acid. It's an electron pair acceptor. The boron in BH3 only is sharing a total of 6 electrons. So it has an empty p orbital that can take a pair of electrons, and we'll see that when we get to boron's molecular orbital diagram for BH3. Borane is more reactive than methane, so hydrogen has slightly greater electronegativity than boron. It's got 2.2 versus 2.0. So each of the hydrogens in borane is really hydride-like. It really has a delta minus characteristic. We're used to seeing hydrogen in water where it's more of an electrophile, so more electropositive, because oxygen's more electronegative than hydrogen. But this is kind of an interesting form. You can tune atoms different ways depending on differences in electronegativities for the things that the molecules that are using them in bonds. So how about the methyl radical? So methyl group, it's neutral, so carbon has 4 valence electrons when it's neutral. Each hydrogen brings 1 valence electron. We end up with 3 bonds, 3 carbon-hydrogen bonds, and then a leftover electron on carbon. That's a radical, and radicals are very reactive. We'll see radical chemistry first when we start doing chemistry in a later video. A molecule with an odd number of electrons is a radical. They're reactive, as I said. You could even think of reacting a couple of methyl radicals to form a bond, as we have symbolized with these single-headed arrows coming together, and we've combined 2 methyl radicals to form ethane. And we'll talk about naming, basic hydrocarbon molecules here soon. How about H2CCH2? Well, we could try assembling a Lewis dot structure such that we form bonds between each terminal carbon and 2 hydrogens, and then the carbons, the atoms themselves, but then we're left over with sort of 1 electron on each carbon that's sort of off on its own. So what I've drawn here is we're going to combine them to make a pair of bonds between the carbons, and so we come up with a double bond, and we'll take a deeper view of this double bond here soon, but we can see we've satisfied carbon's octet in this arrangement. Similarly, for HCCH acetylene, we come up with a Lewis structure showing a triple bond between the carbons. I think that's probably enough for this video. We'll go ahead and continue with practicing in the next video segment.